So we finished about morphology of lakes, and now we're going to go into some of the ways that lakes mix and water moves in them. And the first part of this is stratification. This layering based on differences in density, and these can be driven by temperature differences or salinity differences. Stratification alters the biogeochemistry and ecology. And probably the most extreme way is when oxygen disappears out of the lower layers of the lake. A lake with all the same temperature is called isothermal, right? So that's iso means the same, thermal temperature. And if a lake is thermally stratified, it will have 3 layers. The names of those 3 layers are the epilimnion for the surface, the metalimnion or thermocline for the area where the temperature is changing rapidly, and the hypolimnion, the deepest area. We can use other words that you know to help you remember this. So epidermis is the upper layer of skin, right? A hypodermic needle sticks deep down into you, right? It's deep, hypo, deep. And meta means middle. And limnion is lake. If we look at this graph, and again on the, what is the independent variable on the y-axis now going with depth down to 25 meters, we see that a typical lake in the summer that's this deep in the temperate zone would have a temperature down to, you know, maybe 5 meters or so. And this is typical with what we saw at the Potawatomi State Lake. Number 2, and then the metalimnion starts, where you get this rapid temperature decline. And actually the lake that we went to in the first field trip sort of stopped right here at 9.5 meters, and it looked just like this. It didn't get isothermal in the deep. And then the deepest part of the hypolimnion is down here, and it's relatively colder than the upper part. So here's another way to look at this. The graphs on the bottom are just replacements for that graph that we saw in the last slide. But the graph on the top is a way that limnologists use to show seasonal trends or temporal, right, time trends in a lake. So this particular lake is 14 meters deep. And we see that in the springtime, it's mostly isothermal. So it's mostly green and a little bit of blue. So sort of between 5 and 10 degrees C. And the graph that corresponds to that has almost the same temperature, 7, maybe 6 degrees, all the way down. Then when we come into the center of the summer, we get a hot surface, an epilimnion, a metalimnion, and a hypolimnion. And so we have a graph that looks like that. In the fall, it becomes isothermal again. And in the winter, it actually, you can have another stratification because something is keeping mixing from happening. And that's up on the top of the lake. What would that be?
Wind? The ice?
Ice, yes. So what is it that moves water in lakes? What is it that mixes water in lakes?
The wind.
The wind, correct. So if an ice cover forms over a lake, it cannot stratify. So we'll go through this. This is a dimictic lake from a temperate zone in an area where it freezes. Dimictic means, di means 2, mixus means mixing. We can start in the springtime here where it's isothermal, and it will be heating up. The surface of the water will be heating from the sun. And as it gets warmer and warmer, at some point, the wind can't create enough power to mix that warmer, less dense water with the cooler, denser water. And at that point, the epilimnion depth is set. And it's very difficult to disrupt that depth after that point. So the surface will continue to heat up during the summertime, but the bottom will stay cool. And then in the fall, the lake will start cooling. And the reason for that is mainly evaporation. that as the water evaporates off the surface of the lake, it takes a lot of energy out of the lake and it cools it significantly. At some point, it will cool somewhere right in here. It'll cool to the point where the wind can mix it, and it'll mix it all the way down to the bottom. Right, so it'll allow the temperature to become the same. In addition to that, as the cool weather cools the water at the surface, what happens to that water that cools on the surface?
Does it sink?
That's right. So not only evaporation is cooling the water at the surface, but also the cool air is basically transferring heat away. So the water will sink, and so not only the wind mixes it, but also the increased density of the cool water will force it to move down. As we move into this coldest part, right, where this falls below 4 degrees C, what happens to the water that's cooler than 4 degrees centigrade? Is it denser or less dense than the water that is 4 degrees centigrade?
Less dense.
It is less dense. Remember, the maximum density is about 4 degrees. So all of a sudden, you get this cool water that can stay sitting on top of the 4-degree water that's below it. And then if it gets cold enough and you have a windy, wind-free day or night, then a skim of ice will form over it. And once the skim of ice forms over the lake, then the wind can't mix it anymore. So it'll continue to cool at the surface and the ice will float on top. And then in the spring, the ice melts off, the sun starts heating the lake, and it starts the process again. So you saw that in the laboratory when you worked on that on Tuesday, and Ann talked to you about it a little bit as well. So I mentioned that the thermal stratification is pretty difficult to break. This is a Lindley Pond on the east coast of the United States. It was one that G. Evelyn Hutchinson studied, who we saw in the biography in the very first chapter. Before there was this hurricane, there was a stratified, fairly deep pond. It was stratified. When the hurricane came, it pushed the epilymnion down a little bit. It pushed the temperature of the water by mixing that a little bit, but it still didn't break the stratification, and that stratification held through that event. So that just gives you an idea of you know, how much energy it takes to turn that over, turn that lake over. So monomictic means it mixes once a year. Amictic lakes never mix. So saline lakes are an example of that. If you have a saline hypolimnion, a more saline, remember the density of water related to salinity is even much more dense than the temperature differences. So for example, ocean water, which is maybe less saline than some saline lakes, really is difficult to break stratification. You can have a much cooler water sitting on the surface of warmer water that's saline like that. Polymictic lakes mix several times a year, so we might have some areas that you'll see that, maybe in the subtropics where wind can mix it, or we can have temporary stratification that can come back. Dimictic mixes twice a year. Related to that, our lakes around here, let's say Potawatomi State Lake number 2 that was stratified when we were there this summer, do you think that is a monomictic or a dimictic lake, and why? Dimictic. Okay, Casey says dimictic, and Tom does too. Sometimes it is, sometimes it isn't. When would it not be dimictic? It stratifies every summer. Right. If it freezes over, it is dimictic, right? So some years it's not cold enough in this part of the country to freeze the lake completely, ever, in the winter. And then the lake becomes monomictic. It only mixes from fall, it mixes all the way from fall to spring, right? And then it stratifies. If the ice forms, then it's dimictic. It's stratified again with cooler water and ice on top and then below. In contrast, Tuttle Creek Reservoir is very large, And it never stratifies during the summer. So it may be monomictic in the sense that it mixes all year round, always mixing, or it might have a period where it's stratified if there's ice formation. That's only happened once in the last 20 years or so because the lake is so large. It's very difficult. Okay, so here's a question of the day. Many of the tropical lakes that we see are amictic. So they are not able to mix, even though they don't have this seasonal nature, right? So why do you think that is that they're amictic, even though temperature doesn't seem to vary that much over a day? So we got a lot of good answers. Yeah, the temperature doesn't vary very much over a year. So you expect things to stratify at some point because it's still going to be heating up more at the surface than the bottom because of the sun. Another thing that's really important here is that the temperature difference doesn't have to be as great to allow for stable stratification. Because if you go back and remember the relationship between temperature and density, the maximum density is at 4 degrees C, and then the density starts falling off as it gets warmer, and it falls off faster and faster the closer, the hotter the water gets. So the density difference between 5 and 10 degrees C is much less than between 25 and 30 degrees C, right? So that'll also stabilize the stratification. And then somebody mentioned the salts, which is another important point. The nutrients come into the surface of a lake, and algae grows, and invertebrates eat, zooplankton eat that, fish eat that. And then what happens to that stuff eventually? At least a portion of it. Like if a fish dies, or if a zooplankton makes a fecal pellet, it settles and sinks, right? So it's settling out of that upper layer and sinking down into the deeper water, where the microbes break it down and release the materials and turn them from solids into dissolved materials, except for the carbon, which will respire off. So it sinks and it increases the salinity of the hypolimnion as that stuff rains down over time. That also tends to stabilize those lakes and makes them very difficult to mix. So that's a way that tropical lakes are different from temperate lakes. The lakes in the subtropical areas will become more like that with global warming, and will tend to have more and more amictic lakes perhaps in the southern United States that are always stratified. Different things move water and make currents in lakes. And we talked about wind moving water, and we need to cover the idea of fetch, Langmuir cells, and seiches. So the fetch is the longest distance on a lake where wind can act on it in an unobstructed fashion. And it then depends upon the prevailing winds too. So in this case, if the wind's always coming from the south, and the fetch then this would be the maximum fetch. If the lake here always had the same lake always had the wind from the west, then the fetch would be here. The longer the fetch is, the more the lake mixes. So if a lake has a long fetch, do you expect it, once it stratifies, to have a deeper or a shallower epilimnion than a lake with a short fetch?
But wait, wouldn't it have a deeper epilimnion
That's right.
because there's more mixing?
Exactly. So it's just going to take more to get the heat in there to cause that density difference. So if you have a really long fetch, it's going to be more difficult to stratify. This is exactly why Tuttle Creek Reservoir does not stratify, because it's got a really long fetch and it's just not quite deep enough. In contrast, Potawatomi State Lake number 2 has a smaller fetch. It's also down in the there's some trees around it, and it's kind of down in a valley, and the trees in a smaller one, which somebody answered the earlier question, the trees can alter the degree of mixing that's possible in the lake. So there's actually a study there. They went and surveyed a bunch of lakes in Canada, and they showed that when they were deforested, they had deeper epilimnion than the lakes that had forest around them. Once you get to a really large lake, that'll have a minimal effect, but ponds and lakes that does have an effect. So around here, farm ponds can stratify even if they're 3 or 4 meters deep during the summer, if they're down in the valley and they have trees around them. And that's because they have a very small fetch and the wind can act on them not very well. The longer the fetch is, the higher the waves can be. So if you have, this is a graph of the maximum wave height that you can have given as fast as winds ever really get normally. And the fetch is in kilometers here. So when we get in the ocean, you obviously can have incredibly large waves. But even in the Great Lakes, you can have 10-foot waves if it's really, really blowing. Tuttle Creek Reservoir is able to have about a 2-meter wave, which is about a 6-foot wave, which is a pretty good wave. If you just have a really strong north wind, it would be hitting it on the dam because it has a north-south orientation. Oops. So that brings up the idea of how wind actually moves water in lakes and how that mixing actually occurs. In this diagram, it shows the wind is coming basically from our point of view down along the lake. And when it does that, it is pushing the water on the surface of the lake forward. Well, if it pushes the water forward, the water has to make up for that somehow, right? Because you can't just displace the water and have it go away. Then water has to come up to make up for that, right? So what happens is, as the water gets pushed forward, the water comes up in certain bands, and then the water has to replace that, goes down in other bands, and it causes these spiral mixing. And the spirals are going in opposite directions. So if you just had some kind of chemical tracer in the water, and you can put dye in or something and watch it, it'll mix. And in this cell, it'd be mixing, as it flowed away from you, it'd be mixing down, and then it'd come back up and down and come back up to get these spiral patterns. When that happens, things that are floating on the surface, where the zone of convergence is, right, where those two things are coming together and going down, the floating things get pushed into that line and they can't go anywhere. So they're stuck there, right? Then that's actually a physical thing you can see that's related to that. So this is another picture of Quake Lake in Montana. Remember, we talked about this is a lake that was formed, you can see, where the earthquake caused the landslide to come in here. But the wind is coming, I'm not sure if it's coming with us or away from us here. Can't quite tell. It's coming toward us, I believe. You can see those Langmuir streaks, right, where those spirals are going down. So now when you go across the Tuttle Creek Reservoir Dam and look at it on a windy day and you see these streaks, you'll know what they are. They're showing you the physics of the mixing of the lake. And then the other thing that can happen with this is seiches can form, and it can cause entrainment or some mixing of the hypolimnion with the epilimnion. So in this case, in A, we have an epilimnion and a hypolimnion in a calm lake. In B, we have a sustained wind, and this could be going over days, and it pushes the epilimnion over to the far shore. the hypolemnion has to come up to make up for that. So it causes this wedge to form. If it keeps mixing and really blowing, it'll actually, once this gets up close to the surface, it'll start mixing that cold water into the lake, and maybe some of the warm water will get mixed down into the hypolemnion. So this can be really important in bringing nutrients up. This hypolemnion is very stable, and it just can't mix. The diffusion it's not mixing turbulently, right? There's not eddy transport. So the only way that things can diffuse is molecular diffusion. And we know that molecular diffusion is very slow. If this happens, then you can get eddy transport and you can get some movement. Now the wind stops, and all of a sudden there's this denser water here that's higher than the denser water here, right? So it's going to try to get back even. And when it does that, it starts to rock. And this is called an internal seiche. And over time, that will dissipate, but it can go for days, weeks, a long period of time. You know, I've experienced this straight up when I was on Flathead Lake. There's times when it's a north-south lake, but there's times when there's really heavy winds coming out of the east, and they come down the face of the mountains onto the lake and across. And I used to like to swim there in the summer, but I was on this shore, and this happened. And so all of a sudden we had water that was 5 degrees C coming up, and that's cold water, right? So that cut the swimming off. All right, so this is an internal seiche, and you could see that in the lab stuff. I encourage you to go back and look at the stratification videos and that Stan Gregory made from Oregon State University, because he really lays this out clearly.